Hey folks, Ms. Gosling here. In this video, you're going to learn about nuclear decay. By the end of the video, you'll be able to define nuclear decay and solve nuclear decay problems. So with that, let's go ahead and get started. So in the previous video, you learned about half-life, and you learned that it was the time that it took for half of a sample of a parent nucleus to undergo nuclear decay and turn into a daughter nucleus. In this video, you are going to learn a little bit more about what nuclear decay actually looks like, the mechanisms it can go through, and why it happens. So nuclear decay occurs when the nucleus of an unstable atom spontaneously changes its nuclear configuration. This occurs because it's going to increase the nucleus's stability. So in this graph on the lower right here, you can actually see the curve for the stability of different nuclei. So we can see that our hydrogen 1 nucleus, hydrogen 1 nucleus is a little silly, right? Because it's it's just a single proton with an electron traveling around it. So it doesn't really have any stability or instability. But as we start to increase our number of nucleons, and I do want to mention here, guys, when I say the word nucleon, which you're going to hear a lot this unit, that means the combination of protons and neutrons. So anything that makes up a nucleus, hence nucleon. So you can see here, some of our atoms are significantly more stable than others. So our smaller atoms and our heavier atoms are less stable than some of our atoms in the middle. And you can actually see on this graph, it's labeled here, iron 56 is in fact our most stable nucleus. And we're going to talk more about why that is later in one of our other videos. So nuclear decay happens because increasing the stability of the nucleus is, now I don't want to use the word beneficial because that suggests that there's some sort of choice involved, but nuclei tend towards increased stability as the universe tends towards increased stability. So our parent nucleus is going to undergo nuclear decay because it, quote unquote, wants to be more stable. And again, wants is really not the right word to use here, but I can't really think of a better one right now. So let's talk through the different mechanisms for nuclear decay. And there are 4 key mechanisms that you need to know for this class. So the first mechanism for nuclear decay is something we call alpha decay. And in alpha decay, an alpha particle, which is a helium-4 nucleus, and note this is sometimes written just as an alpha, like so, is going to be released. A good example of alpha decay is the decay of U-238, uranium-238, into thorium-234. And you can see here our numbers all balance. So we start with a total nucleon number of 238, and we end with a total nucleon number of 238 as well, 4 plus 234. Similarly, we end with the same number of protons that we started with. So uranium-92 starts with 92 protons, and those 92 protons are split in the end between 2 in our helium and 90 in our thorium. So in our first example of alpha decay, the total nucleon number of our particle is going to remain constant, and the total charge is going to remain constant. So we have we are neutrally charged. We're going to start with 92 protons. We're going to end with 92, the total charge of 92. Our next 2 kinds of decay are similar to one another. So we're going to start with beta decay. Now this is also known as negative beta decay or beta negative. And sometimes instead of seeing an electron written out, you'll instead see beta negative. And we're going to so in negative beta decay, an electron is released. Additionally, something called an electron antineutrino, which we will get into later, is also released, and that's just a part of ensuring that our momentum is conserved. So a good example of beta decay, of negative beta decay, is when iodine-131 decays into an electron, into xenon-131, and into an electron antineutrino, which we're going to use V bold to represent. Well, nu bold, really. And you can see on the bottom, again, our numbers continue to add up. So we start with 53 protons. That's going to turn into 1 electron and 54 protons. So our total charge is still going to be 53. Hence we can see that that kind of charge is conserved in this situation. So the next kind of decay is so similar to beta decay that it's actually often just called positive beta decay. The IB likes to call it positron decay, so we are going to use that right now. So in positron decay, an electron and a positron, so a positron is an electron, but instead of being negatively charged, it's positively charged. It's actually the anti-electron is another word for it. That is going to get released, as will an electron neutrino. And again, the electron neutrino we're not going to worry about. It's just there to help conserve our momentum. A good example of positron decay is when carbon-11 decays into a positron and boron-11. And so we can see again, we have all of our masses adding up and all of our charges on the bottom adding up as well. Our final kind of decay is the hardest to see. So because it doesn't actually have any particle get released. Instead, we just have energy that's released. So our last kind of decay is called gamma decay. And in gamma decay, our particle is going to go from one nuclear configuration to another, and it's not actually going to the particle itself is not going to change. So we're not going to have any new elements. We're not going to have any new electrons. We're not going to have any helium-4 nuclei. Instead, some energy within that nuclear configuration is going to be released as gamma radiation. So we'll have a more stable nickel nucleus. Again, we still have nickel, and we'll also have some of that gamma radiation. And we're going to represent a less stable configuration with an asterisk. So we're going from nickel unstable to nickel stable. So let's go ahead and talk through a few examples. So in our first example, thorium-234 undergoes negative beta decay. What nuclide will be generated as a result? So I'm going to let you know, when you're doing these problems, you probably want to have a periodic table handy. So we're going to look through our periodic table, and we can find thorium here at number 90. So we're going to start with thorium-234, 90, and that's going to undergo negative beta decay. So I know that an electron with a mass of 0 and a charge of -1 is going to get released, as well as an electron antineutrino. Now I just have to balance the top and the bottom of my equation. So our mass is going to stay the same at 234, but we're going to have element number 91, which is Pa, otherwise known as protactinium. So we're going to have protactinium 34 get generated as a result, so that our subscripts add up to 90, because 91 minus 1 is, of course, 90. So the nuclide that's going to be generated as a result is Pa23491, or protactinium 234. Either of these is perfectly acceptable to say. I usually stick with this one because it's easier. So moving forward to another example. So this time our thorium-234, which of course still has an atomic number of 90, is going to undergo alpha decay. So a helium-4 nucleus is going to get released. And we want to figure out what the daughter nucleus will be. So one of our daughter nuclei is, of course, our helium-4. But our other daughter nucleus is going to have a mass of 230. It is going to be atomic number 88, which we can see here is radium-88, or radium-230, which is atomic number 88. So again, our daughter nuclei are helium-4 and radium-230. So third example. This time we have strontium-90, which is going to have atomic number 38, as I can see in my image over here. And we know that strontium-90 is going to be decaying into yttrium, which is atomic number 39. So looking at our 4 kinds of decay, we know it's not alpha decay because we're not decreasing our atomic number by 2. We know it's not positive beta decay because we're decreasing our atomic number by 1. And we actually know that it has to be negative beta decay. So that way we can balance out the right side of our equation with the left side of our equation. So because of that, we know that an electron and an electron antineutrino are both going to be released. And we know that our atomic mass must stay the same at 90. So here is our nuclear equation for the decay. And one thing that I need to make sure I add here, and that I want to make sure I add, is a bar above my electron antineutrino, and that's just how I'm going to differentiate between my electron antineutrino and my electron neutrino. So with that, let's go ahead to our last example. And we're going to look at iron 55 capturing an electron. So in this case, so we know that iron, Fe, is here on our periodic table, so it's got atomic number 26. And we know that it is capturing an electron. So the electron is actually going to be on the left side of our equation rather than the right side, because it's something that we are starting with. So what we're going to do is we're going to start with an iron nucleus and an electron. And we're going to end up with something with the same charge, but with atomic number 25, giving us manganese instead. So here is our nuclear equation for electron capture. And again, this isn't nuclear decay in the state. We don't have the nuclear radiation that we have in other situations, but this is another example of nuclear decay where we're transitioning from a more stable nucleus, or from a less stable nucleus to a more stable nucleus. So with that, let's talk takeaways. First of all, unstable nuclei undergo radioactive decay. And there are 4 kinds of radioactive decay: alpha decay, positive beta decay, negative beta decay, and gamma decay. We also can have, of course, our nucleus change through electron capture, which is different from our other 4 kinds of decay in that the new particle is going to be on the left side of our equation rather than the right side of our equation. So with that, it is your turn to try solving some nuclear decay equations, try balancing them out on your own. Best of luck, and happy solving.